Hi students, we're going to keep going on chapter 17. This PowerPoint's not from your textbook, and I hope you don't mind that. It is linked to the worksheets we've been doing in the Zoom, and I just like looking at this section in this way. And please use your book as a supplement, obviously, and I will be posting the ones from the book on this part. So let's go ahead and take a look at where we're at. Second law of thermo says that for a spontaneous process, one that does not require any sort of outside intervention, the delta S of the universe is greater than 0, meaning that the entropy of the universe increases. Now, delta S of the universe is delta S of the system plus delta S of the surroundings. And one thing to think about, and I think it's fair to think of it logically, is that delta S of the system, sometimes we can predict by looking at what's going on in that process. Is it going from a solid to a gas? Is it going from a liquid to a solid? What you want to think of is that delta S of the system will increase and be positive if we're increasing the number of microstates in that system, and how they can arrange and organize goes up, right? The possibilities increase. So in other words, you're looking at an increase in randomness. Oops, I didn't spell random right. It's an N there. Okay, so the other thing that we learned from the previous PowerPoint video is that delta S of the system can be found from the tables, right? Using the tables in the back of the book. And then products minus reactants using the coefficients. Okay, and that delta S of the surroundings is a different discussion, that when heat flows, so here's your system, here's your surroundings. When heat flows from the system into the surroundings, then you'll see an increase in the entropy of the surroundings. So the surroundings depend on whether it's endo or exothermic. And so we have an equation for that. Okay, now there is an easier way of discussing spontaneity, and that is free energy. That the delta G of the system, if it decreases, it's giving off free energy to do work. So if delta G of the system is negative, it's releasing free energy to do work. And so that process is spontaneous. So I love the example of your cell phone battery, the lithium-ion battery. It's releasing free energy to do work, to power your telephone all day. And that's a spontaneous process, highly reactive, product favored. Okay. When delta G is positive, it means that it needs outside intervention to make that process happen, because it's not spontaneous. So in the case of your cell phone, at night when it dies, we have to plug it into an outside current. That would be a process that requires free energy. Okay, and we'll be talking more about batteries in the next chapter. One other thing before we move to the next slide is that I know you've been noticing these not symbols. That means Those are under standard conditions using thermodynamic tables in the back of your book. So usually these will all have that because that's all we're going to be using to calculate the delta G's. To calculate the values, we use those tables, and those are under standard state conditions. One other thing is that these two are different ways of looking at it, but they are the same, and we'll see why in a second. The delta S of the universe greater than zero business, I would say, is used more in physics and engineering, whereas the delta G discussions tend to be very popular in chemistry and biology. I'd like you to know them both routes, but I want you to know that, well, personally, I feel that delta G is a much easier way, and I'll convince you of that in a few minutes. Okay, so Gibbs-Helmholtz is delta G equals delta H minus T delta S. And so when delta G is negative, it's spontaneous. So one of the key ideas is that spontaneity depends both on enthalpy and entropy. So spontaneity, right, whether it's spontaneous or not, depends on enthalpy and entropy. Okay, then you need both. Now, where did this equation come from? Let's take a look at the delta S of the universe equals delta S of the system plus delta S of the surroundings, and then we can make a substitution. So delta S of the universe equals delta S of the system, and delta S of the surroundings, remember the equation is negative delta H over T. Okay, and that's whether it's endo or exothermic, and the temperature decides that the value of delta S of the surroundings. If I take this equation as written and multiply through by negative T, we end up with negative T delta S of universe, negative T delta S of system, plus delta H of the system. And then notice what will happen is that what happened was they defined negative T delta S of the universe. That is our free energy change. And then we just switch it around to make delta H first minus T delta S. And for us, we're really looking at standard state conditions. Why do I like this equation so much better? Is we don't have to deal with that business of the surroundings. Everything's based on the system. Temperature is shown very, very clearly there. And so I just think it's significantly easier. Okay. So this is the worksheet. I'm hoping that you have it printed out. And so I'm going to go through this one. Okay, now I wanted to say one thing that you need to have your tables from the back of the book handy. So if you could get those out, that would be great. And then I'm going to get the values out for this reaction so we have them available. And so I'm going to look for the oxygen one, which I believe was back here with ozone. Your book is not so great. It's kind of an abridged version. Oh, I found it. Okay, so for O2 in the back and O3 in the back, they'll have delta H of formation. They'll have delta or S of formation, or not formation, sorry. Sorry about that. So it'll have delta H of formation and then the entropy values. And then it's going to have for oxygen, this will be 0. For ozone, this guy's 143. For entropy, 205. And for ozone here, 239. Okay, let's note the units. For enthalpies of formation are in kilojoules per mole. And for entropy, those guys are in joules per Kelvin per mole. Okay, now why did they decide to switch those units on us? It's really because of the numbers. You'll see here in a second that the entropies are pretty small, and so they make more sense in describing them in joules than kilojoules. But we'll see that here in a moment. Okay, let's start with scenario 1. The formation of ozone from oxygen. Okay, there's our equation of interest. Can we predict the sign of enthalpy? Probably not. We don't know if it's endo or exothermic. If I want to know, I will use the thermodynamic tables in the back. I'll do this first one here. So I'm going to take 2 times ozone. So that's our product, right? And then I'm going to subtract off 3 times 0. Notice I got a little lazy. This should be moles there because that's going to cancel with the moles. Okay, so 2 times 143 should be 286 kilojoules. Okay, now the question is, that's our enthalpy for our reaction. Okay, endothermic. So this is an endothermic process. Okay, now what happens to the entropy of the surroundings? Always, here's our system, here's our surroundings. If heat flows into the system, the surroundings molecules are going to start to lose energy, slow down, and we'll see a decrease in the entropy of the surroundings. I can actually calculate a value for that, and the equation always for delta S of surroundings is negative delta H of reaction over T. So here's my delta H, 286 kilojoules, negative of that divided by 298.15. I'm going to assume all of the examples I do are at 298. So here's my entropy of the surroundings, negative 0.960 kilojoules per Kelvin, which is the equivalent of 960 joules per Kelvin. Okay, so if we take a look at that, what are we looking at there is the idea that this is negative, and it's not a surprise because always endothermic processes are accompanied by a decrease in the entropy of the surroundings. Okay, now let's talk about the system. So we have the surroundings done. So this part here is done. Okay, now let's take a look at the system. It's going from 3 moles of oxygen to 2 moles of ozone. So we're going from 3 moles of gas to 2 moles of gas. That means the number of microstates is decreasing, and so the entropy of the system's decreasing. That's my prediction. And I can use the thermodynamic tables in the back to come up with this value of delta S of the system. Okay, I can go ahead and calculate that. Okay, and we plug that in, is come out with negative 137 joules Kelvin. Okay, now we're going to pull this all together. We're going to say, what is this spontaneous or not? And for that, I need my delta S of the universe. And I would add the entropy of the system, which I just got, plus the entropy of the surroundings. Now, one of them's in joules Kelvin, the other one was in kilojoules Kelvin. So I would have to convert them to be one and the same unit. Doesn't matter which way I go. When I do add them together, and you can double check me, I end up with a negative entropy of the universe. That means it is not spontaneous. This process is not spontaneous. I can double check it by determining the free energy. So using Gibbs-Helmholtz, I take my delta H, this value is delta H, and I would do delta H minus T delta S. I want them in the same unit. So I went with kilojoules this time. And I ended up with a positive delta G here. And again, that means not spontaneous. Okay, now the overall picture is that if a process is endothermic and the system decreases in entropy thermodynamically, this will never be spontaneous. You will always need to provide an outside constant source of energy for this. Okay, next situation. Exothermic and increasing entropy of the system. So here's a scenario: hydrogen peroxide decomposing into water and oxygen gas. Would you predict the sign of the enthalpy? Probably not. We really don't know if it's endo or exo at this point. So I would find delta H of reaction. This would be using the tables in the back of the book. Now, I'm not sure if your book has these particular species in it. So if not, you could go reference the internet. Obviously, on your test, I'd have to give you the values. What I want you to realize is here's the number, negative 196, exothermic. Exothermic values, exothermic reactions. Heat flows from system to surroundings will always increase the entropy of the surroundings. I can calculate it always by negative delta H over T. So if you could take a moment to do that and double check me, that I would end up with 0.657 kilojoules per Kelvin or 657 joules Kelvin. The system now, let's take a look. We're going from a liquid to a liquid and a gas. So we're releasing a gas. So that should increase the entropy of the system. And then using the tables from the back of your book or from a reference, we would see it's 125 joules Kelvin. So for sure, we're seeing an increase in the entropy of the system. If we plug this in to our delta S of the universe equals delta S of the system plus delta S of surroundings, we will end up with 782 joules Kelvin. Notice it's positive, which means spontaneous. And delta G is negative, negative 233, spontaneous. And if we look at our overall equation, notice what happens with just the signs. If this is negative and delta S is positive, a negative minus this positive will always be negative. And so this type of reaction, an exothermic and increasing entropy of the system, is always spontaneous. It will occur without an outside intervention that is constant. So these reactions for us experimentally are easy to do. Okay. Scenario 3, endothermic and entropy of the system is increasing. So in this case, this is N2O plus oxygen to make 4NO gas. Could I predict the sign? I might predict that it's exothermic because it's a combustion. It didn't prove to be true in this case, but if I ask you ones to predict, there'll be ones that are easier to predict. Okay. And then calculate the delta H of reaction. Again, back of your book. I doubt these are back there, but here, if you had thermodynamic tables, you can find it. So for this one's endothermic. Endothermic, always, because negative delta H over T, endothermic reactions are always decreasing the entropy of the surroundings. Okay, you could calculate the value of that. Okay, so we would take negative 197.1 kilojoules over 298 Kelvin to come up with the value. So let's see what we get. .661, negative 0.661. What do we predict the sign of the entropy, and I'm going to put of the system to be? So let's go to our reaction. They're all gas phase. I have 3 moles of gas to 4 moles of gas. So I predict that we'd see an increase in entropy of the system. And using thermodynamic tables from the back of the book, here would be the value that you'd get, products minus reactants, taking into account the coefficients. Okay, now this one's interesting because now you have delta S of the universe equals delta S of the system plus delta S of the surroundings. The surroundings value is negative. The system is positive. They're battling it out to determine what's going on with the delta S of the universe. What is going to decide that will be how big the numbers are and what temperature you're at. Because the temp, look at down here, the temp decides the magnitude of delta S of the surroundings. Now, I personally think it's a lot easier to picture this with the delta G equation. And if you don't mind, I think I'll go to the next slide. I gave myself some more room. And let me go back real quick. So this was endothermic with an increasing entropy. So this is plus for this and a plus for this. Now notice they're going to be pulling delta G two opposite directions. The enthalpy, the heat, I guess you'd say if it had feelings, wants, I'll put that in little quotes, to make delta G positive. But the entropy term pushes to make delta G negative. Who is going to decide which one wins? Temp. And if I want to know the magic number, the magic temperature where it crosses over, then I think about this, that this term here is in contrast or opposing G delta S. So I'm going to set those equal to each other. And temp will be delta H over delta S. Now I need to pull, oh no, I wrote down those values. Delta H for this one was 197.1. That was kilojoules. And the entropy was 198.2 joules Kelvin. Now be careful, we have to get them the same, so I'm going to divide this one by 1,000. Notice the joules business cancels, and the Kelvin will flip up to the top. Sorry. So 994 kelvins. Now, what I like to do is I like to think of this kind of in a number line viewpoint, where here's my crossover temp, 994 kelvins. That's where it crosses over. And now let's think, okay? To make this delta G negative, we want this term here to win, right? We want that term to win. And so temperatures above this number will be spontaneous. The process will be spontaneous when it's above that temp. If you're below that temp, it won't be spontaneous. Because the highlighted term here won't be big enough to compensate for it being endothermic. Okay. All right, let's go to our last scenario. Exothermic and entropy of the systems decreasing. So can we predict the sign of this one, sodium plus chlorine to make sodium chloride? I don't think so. It is, and sorry, I got a message that my computer's going to die. Okay, so what do you predict would be the sign of the enthalpy? Not sure. Turned out by using thermodynamic tables. So again, using the tables, it is exothermic. So exo, pretty large value too, very exothermic. So what do we mean? What would it mean? Delta S of the surroundings, and entropy of the surroundings would be negative of that. We expect when the surroundings gains all that heat, its entropy for sure is going to go up. Sorry. So we end up with 2.758 kilojoules Kelvin. Okay, and it's plus, as we expected, heat flowed from the system into the surroundings, increasing delta S of the surroundings. Okay, what would we predict the sign of the entropy to be of our system? Let's go look at the reaction. We have a solid plus a gas going to a solid. So that gas going to a solid is really, we're going to see a decrease in the entropy of the system. Do you see now how they are opposing each other? They're opposing. This one's increasing and this one's decreasing. Since they're opposing each other, the temperature will decide. Okay, here's the value for the entropy of the system. That'd be from the thermodynamic tables, products minus reactants. Okay, so I'm going to give myself some room here. I think temperature dependency is a lot easier to see with Gibbs-Helmholtz. Okay, we had a very, very exothermic reaction. And then the entropy was decreasing. So you see how they're opposing each other? So the enthalpy wants to make delta G negative, but the entropy is working against it, right? Is making delta G positive. So who's going to win? The temperature decides. Okay, and so again, how are we going to figure out that temperature that it crosses over? We are going to set these guys equal to each other. This term versus this term, because the magnitude is going to decide it. T will equal delta H over delta S. And then I have the numbers, negative 822.2, that's kilojoules, over entropy, negative 181.7 kilojoules Kelvin. Was that kilojoule? No, that was joules Kelvin, sorry. I couldn't read my own writing. Let me erase it. Joules Kelvin. 1,000 joules and 1 kilojoule. Okay, so let's see this value. This is a really strange number. It's pretty big. Oh, yeah, I guess it is. Let me just double check it. It's just kind of weird. It's because it's super exothermic. That's why we're seeing such a dramatically large number. Hold on, I'll explain in a second. Let me just punch it one more time. I keep, sorry. You probably are done now. Yeah, so that is correct. Now let's think about this. Okay, that ridiculously high temperature. And so let's take a look. In this case, if we want delta G to be negative, we would want temperatures below this number because we want delta H to be dominating. So below that temp, this is going to be spontaneous. Above, not spontaneous. A reaction like this is said to be enthalpy driven. Because the enthalpy wants to make delta G negative. And so it's really pushing that value to be negative. Okay, whereas in the previous one, in our previous reaction, see if we can go back. The entropy is pushing it to be negative. So this one here is more entropy driven. The other thing you'll notice is in this first temperature dependent category that we did, temperatures above that calculated temperature make it spontaneous, whereas in this other category, temperatures below that make it spontaneous. Okay, so the big picture then, and I like it with the delta G. I just think it's so much cleaner. The way that I presented it, it's not an official thing on scenarios 1, 2, 3, and 4. I mean, they could be numbered anyway, but the way that I did it, the first scenario that we looked at, you had an endothermic process where the entropy of the system was decreasing. And that means that delta G is always positive, never spontaneous. And those are processes that would be really difficult to do experimentally. They're going to require an outside source of energy. In the next chapter, we'll look at that in the context of like recharging batteries or maybe taking like water and making elements from it. You have to put a current through it. Okay, the second scenario that we looked at was exothermic, where the system becomes more random. And in that case, that was always negative, always spontaneous. Now, I'll stop here for one sec because as a biochemist, these two really are always present in the body because there's a lot of processes in the body that are not spontaneous. So like muscle contraction's a good example. And so to contract our muscles, that is a mechanical process that needs free energy to be supplied. And where does it get it from? It's in the body. There's usually a not spontaneous process is linked to a process that's spontaneous, like the hydrolysis of ATP. So that's called reaction coupling. So in biochemistry, we need this information because there's many processes that are in this category of not spontaneous. How do we make them work? How do we get them to go in the body? Is they're coupled. They're coupled to one that's always spontaneous. Okay. All right. In a chem lab, how do I make one that's never spontaneous? The best examples I can give you is currents, that we apply currents to water to get elements out. That's called electrolysis. Okay, the last two we did was endothermic, where the entropy was increasing of the system. This was temp dependent. And then the other one, the last one, was exothermic, where this was negative. That one's also temp dependent. And if I'm looking at for the one that's endothermic, where this entropy is increasing, we want this term here to be very big. So that one's we're gonna find that those are spontaneous at higher temperatures than the temperature we calculate from delta H divided by delta S. And then in the other category, the last one, okay, where this is exothermic and this is the entropy is negative, we want the enthalpy to win, correct? So usually those are spontaneous at temperatures lower than that transition temp. It all depends, though, on how big the numbers are, right, for enthalpy and entropy. Okay, every single reaction you've done falls into one of these categories. And then other things, too, to think about are that they'll only ask you for a temperature dependency for these two, for these guys. Temperature doesn't apply to the top two.